Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is basically the artistic summary of the whole talk now. So if you already get it, you can already leave, that's fine. I will be talking about what is performance analysis and why ground truth is important and how we can generate ground truth. And first of all, I will put credits for my students down here. I will mention them every now and then so you see who was involved in which project. There are many things, like 6 most important things to define what is actually performance analysis. And I think everything starts with a very accurate problem definition. And I argue that, and I try to be provocative, that most techniques like optical flow or segmentation are not really defined well. And this is like more a question to you, so please don't hesitate to challenge this hypothesis. But for example, for optical flow, I'm very sure there's particle image velocimetry, there's medical image registration, it's all the same, but it's also everything very different, and we have different models and so on. So this is the first step. Then I'm pretty sure we need to have the application in mind, and it depends on how we really define the application. One definition might be that we just say we want to solve the problem of constant albedo moving objects. That would be fine, it could be an application, but another application could be a driver assisting system. And there these assumptions do not hold. So we have to be very clear about the assumptions, and we have to be, which is also encoded here, but we also have to be very clear about our requirements. And I would say that jumping down here, a single or a scalar performance measure will not help to evaluate all the requirements. We might have a set of 10 or 20 requirements for an optical flow algorithm, and some of these requirements might be met and some of them not, and we need to know which of these algorithms can we choose. And then there's 3 points, so let's go here. So I will leave these out for today. That's just a few points. I will quickly talk about the model. I will quickly talk about why we need reference implementations and why they are fundamental and why they are a research result we actually need to publish along with the paper. And finally, there's ground truth, and this is the main part of the talk. There is a paper discussing all of these points, and I wrote this paper recently after a Dutch dual workshop, and all these guys have been part of a working group in this workshop, and we sat together actually, so I wrote most of the paper, and then we sat together and refined the paper, and all of these authors basically say we like what Daniel wrote here. And I'd like to strongly encourage you to also read this because it's very interesting. It's not strictly on optical flow, it's basically on performance analysis in general with application to optical flow. So why I'm talking about optical flow all the time, looking at how many publications we have in the past years. Everything started around 1980, and every 10 years the number of publications doubled. It's exponential growth. I've been searching only for optical flow, no patterns, only in optical engineering, computer science, and mathematics. So it's a Google Scholar search. And you will see right now we are at about 3,000 publications. The question is how many of these publications matter, how many of them are useful or meaningful for us. So I also had a look at each of these publications individually, and I found out there are at least 1,400 methods, so new models how to measure optical flow. And I came up with this formula in my thesis. I call it the Konderman formula, if you like it. But it's summarizing all of these optical flow techniques in one formula. So it's basically you just take one location, one model here, plug it together, and you have a new method. This is not perfectly true, but I really tried to capture all models I found, local models, global models. Sometimes you have neighborhoods, sometimes you have motion models relating to a parameter vector, which is not the flow, but a affine model, for example. You can have a sum of different regularizers with different penalty functions, and usually you either have a sum here of several data terms, or you solve this integral. Sometimes it's a Mark-Ferenczi field, but it's basically the same. So there are many methods, and we need to choose the right one. And I use this formula to motivate and the number of publications to show that there's a big need to really see which method applies to my specific problem. The next problem is implementations. During my thesis, this is also part of my thesis, but it has been re-implemented by my students in a better way, a much better way. We tried to implement many algorithms in this modular fashion. So we had this formula, and we saw that we can really plug models together. And here, for example, this is a method by Kincktfusing. I think it's the learning optical flow method. And here you see all the side effects. You have, for example, here you have the solver. Down there is the solver, which is just a linear system solver. And we first create a big linear system of equations. And then we have some iterations over these linear systems of equations because we have to re-linearize. Then there is a data term by Horn and Schunk with a brightness model and a motion model. Then we have here a spatial regularizer by Kincktfusing and the data term and so on. And this is all one model. And in case we now want to change one aspect of the full algorithm, we remove just a part of the model and replace it with something else. So everything else remains constant. The code is exactly the same. And this is a big problem when we want to compare algorithms, because if I take MATLAB implementation A and C++ implementation B, they vary hugely. So we try to do this, and I encourage you to have a look. It's all open source. There's also a full 3D reconstruction pipeline in the code, which is very similar to Visual SFM, which has recently been published. It's open source as well. And there's many, many students. These are 3 of my PhD students working on this topic, but there's lots of interns and undergraduates working on this as well. So these were the first parts, and now I'm going over to ground truth generation, which is my major concern at the moment. This is a scene I will show you. It's probably kind of copyright, digital rights management protected, I don't really know. So I put this source here, it's a movie, Cloverfield. And I hope the fair use, whatever rules in Great Britain are more lax than in Germany. The movie basically shows something where you want to estimate, or you do not want to estimate the motion.
There.
Did I?
Run. Okay, run. Actually, run. Hey, let's start running. Just run. Let's start running right now.
So we see lots of different problems. We see infrared light sources. We see artifacts. We see motion blur. There's all these problems. And if somebody asks, can you generate ground truth? You always have to ask ground truth for what? And that's not only for the application. It's only for the type of data you have to deal with. And I'd say for this one, we don't need ground truth because we can't compute anything on the scene. So let's have a look at the related work. There's the Yosemite sequence from 1994. Here you see the 7 frames of the sequence, and we all know this has been solved. That's no problem. Here, just for fun, I Googled, and on YouTube I found this Yosemite sequence. So this is a real Yosemite sequence. And it just shows differences, conceptual differences. You have light blooming, you have all this shaking camera, vignetting and stuff like that. And this might also be a crucial part. So this ground truth is obviously not helpful any longer. It was very helpful for a while. But this real scene is very challenging. So do we want to go there? Next point is, then we had 2000, and I think 2007 or 2006 was the first publication on the Middlebury benchmark. So it's not the journal version, which you have in, I think, 2010 or something. So here you see one of those test scenes, the Grove scene. And this is a real scene I found on YouTube again. And here you find a scene from the game Crisis. And this game was published in the same year, and here we could theoretically create ground truth in large amounts just by taking the real-time rendered images. And the complexity of this scene is much higher than here, but we still have to ask the question, is our application domain imaging in the woods? Does it make sense? Or do we have flying cameras? Do we usually fly with a camera? Are these motions realistic for our application domain? That's very interesting. And I don't think I have an answer for this problem, but I think we can now try to approach the problem of generating this ground truth with different ways. So there might be reference data without ground truth, and it might be useful, and I will come to that in a second. Then there might be weak ground truth, which is of unknown accuracy. For example, we measured something and we don't know what the variance of these measurements was. This would be weak ground truth. And finally, there would be real ground truth, so we actually know the accuracy is like 1 magnitude larger than the accuracy we can measure with our algorithm. This can be achieved with graphics, and this was very impressive what I saw, what Michael was talking about on Monday. So this is a huge amount of work already. It sounds simple on first sight, just create graphics. But create the content of the graphics, create the renderers or the shaders for creating the ground truth, how to deal with anti-aliasing and stuff like that. There's lots of things in there. And then you still have to ask about the realism of these scenes. Do they make sense for our application or do they not, and how can I evaluate that? Then there's the idea of measurements. So if I have a measurement device which is much more accurate than the data I have, for example, I estimate optical flow on a scene taken with an RGB camera, I might have a measurement device behind it which gives me online 3D reconstructions, and I can use these to get ground truth. And if I know this accuracy, then I'm almost done. Weak ground truth can be created with more data. So we can, for example, as in the Middlebury data set, we created these, or not we, those guys at Middlebury, created these huge images using UV paint. So they sprayed, in a painstaking procedure, they sprayed this UV paint onto the scenes, then recorded the scene once with with a normal light, with regular light, and then with UV light. So we have more data. And we also have the structure in there. And then you have a larger resolution. You can downsample these images if your algorithm is not biased. If it were biased, you can downsample for more accuracy. And that's another option to create ground truth, and it's really very interesting. And finally, there's annotations. So it's difficult to create annotations for optical flows. So for each pixel, you want to have a sub-pixel accurate location where it moved. This might be difficult, but I'm actually trying to find out whether it works or whether we can do it. And if we don't have ground truth, we can use experts. Some people just look at the flow and say, it doesn't work, that's wrong, it cannot be. And then if you ask them why, they will very closely look at it and show the boundaries of the depth discontinuities and so on, and they will see that whether there is a reflection or if there are multiple motions, which motion is estimated, or is it just an average of the motions which have been estimated at this location. So you can, I think you can rely on experts if you have some type of application domain where people are really experienced. So we created such a ground truth data set, and I just quickly skim over it. It's very related to Raquel's work. She also did an impressive job on creating a huge data set, and they even created ground truth. We did not create ground truth. We just recorded data, but it was in a very specific way. So we have 15 data sets, and each data set exists of a number of locations. These locations are, for example, city, town, autobahn, country, and so on. They are triggered via GPS, and they are triggered every time. So we have these 15 data sets recorded during all seasons, monthly, for 1 year. And then we recorded for each data set, we have these GPS triggered locations, so it's always the same or approximately the same location. And at each location, we have 1,600 frames, and we recorded this with 100 Hertz, so it's high-speed cameras, which are quite large resolution. It's approximately the same as Raquel did it, and with 12-bit accuracy. It's an industrial-grade camera, machine vision camera. The data was indexed and annotated. We rectified the cameras radiometrically and geometrically, and there are 2 data sets who are related: Raquel's data set and Mr. Kletter's and Peter data set, which is also very interesting. Next problem is, how do we ask people to work with these data sets? Most people say, whoa, so much data, I'm not interested. Or the data is too difficult, or whatever. So our first try now, this is our first try, is this ECCV workshop, and I would like to invite all of you to take part in this workshop, this year's ECCV. And we also have a robust vision challenge. And this robust vision challenge is about these sequences that you see here. They're stereo sequences. We have downsampled them. We have complex scenes of different types. For example, we had to cut out this scene for privacy. But for example, here you see these snow everywhere in the car, throwing up the snow. Then we have these night scenes and winter, and you have lots of artifacts. And actually what we want to do is we want to encourage researchers to look at stereo and optical flow from a different perspective. This is about detecting when these models cannot work at all. So in these sequences, there are situations where you will never estimate a good flow. Or if you estimate a good flow, then you have very high knowledge about the scene and the world. And this would be interesting, perhaps for confidence measures, estimate when you cannot estimate the flow. Or for methods which just estimate the flow but use high-level knowledge, for example. If we know this is a car, these reflections won't matter. But these reflections on this car will be very problematic if we want to do a photometric comparison of the pixels. So you will find our more details on this URL, or you can just drop me an email. And I also sent this to Image World, and I'd really be happy if you try to work on this data. So again, it's not about getting very good results in terms of a nice optical flow results. It's more about trying out your method and try to find out how your method can be improved to deal or to detect such situations where the model actually fails. This big red box says recalling a lot of data is not selecting representative data. So first of all, we have the content problem. We can record all of the data in the world, and we don't know which of this data is meaningful for our application or for evaluation. This is the first problem. But then we still need ground truth, and for this sequence, we don't have ground truth. So what can we do? One thing, and this is a really bold endeavor, and I'm not sure whether it will work out well, but we are in the fifth iteration now. We take the data, and there's a tool by Sil Liu. He was creating a paper, CPPR 2008, and he created a human annotated ground truth, which was difficult and it was controversial. And it's still interesting, I think, because he found that, for example, at each pixel, at each object, you segment the objects first, and then you track the objects. And after you track them, inside each object, you try to estimate the flow. And these motion boundaries are the major problem, I'd say, in optic flow estimation. So we created this mechanical Turk interface, so you can take Sil Liu's software, edit the first frame, track the scene, send it to Mechanical Turk, then it's improved or worsened, we don't know. And this is the interface here on the web, and then you can edit this. And this is the part, this is an old video from last year. We have some newer videos where we also do the feature matching. So we have interfaces for feature matching, and it's a major challenge, as we just heard here, to get this human into the loop of this kind of image processing. So another option is to create ground truth based on existing assets. And that's what we heard from Michael Black. What we did a slightly different approach. This is Crysis 2. It's one of the most acclaimed games for its computer graphics and degree of realism. This is real-time graphics. We thought, and you see all these problems here, this sun and so on. So we thought, what about the depth channel? We just switched on the depth channel. We render left and we render right views. There are lots of problems in this approach. But we do have this depth ground truth, and we can now let players play this game for hours and hours and hours, and they will, every time they will create new content. We can even design new levels, put them on a multiplayer server. People go and play on this multiplayer server, and we will get as much content as we need. And I think that's a very interesting approach as well. So the main problem is creating content, so having assets which really are meaningful. And in these games, you can say, well, it's a sci-fi game, so there are some assets which doesn't make sense, like UFOs or something. But I think it's also one approach which might complement the other approaches. Then we asked, okay, now if we have these synthetic data sets and real data sets without ground truth, what can we do? Do we really know that these synthetic data sets are comparable to real data sets? And this is very preliminary work, and we noticed there are lots and lots of problems. We published it at a small conference, and we rendered a scene, and we recorded the scene, and we compared the two, or it was sequences. So this is the real image, and these are different renderings with different parameter sets. It's all Blender and very simple renderings, so we are no computer graphic guys. We just tried to figure out how far we can get with that one. And we found out that if we increase the realism in the renderings, and if we have very good geometry, we will get almost the same results from optical flow compared to the real sequence where we have optical flow. but it's only on average. And if we really look at the details, there are systematic biases. So if we take a real scene, we will have other, for example here, this is wood. Wood is a very different material. It's lacquered wood, so there where the lacquer is, we will get reflections, and in other regions we won't get reflections. This induces motions. If we simulate this with computer graphics on this primitive, simple manner as we did it, this will induce motion artifacts. So I still think this is a very interesting approach, but it's a long-term project, I'd say, and inviting everybody doing computer graphics to assist us in this thing. We can do high-accuracy 3D scans, and we have lots of devices from structured light to LiDAR to whatever you need, but we don't know much about this material capturing or using materials and so on. So first problem was we need more geometry. This was handcrafted geometry. What can we do? Now there are two small projects. First of all, we can create ground truth by manual measurements. And this is, from my point of view, the best way because it's the most accurate way if you do manual measurements. For example, take this box, we call it the Heidelberg box. You see all of these discontinuities here at the boundaries. And no 3D scanner can really capture these discontinuities if the scale is too large. You can use structured light scanners and they get very nice boundaries, but a LiDAR won't work and many other methods won't work as well. So a high-end structured light scanner, which is like 50 microns accurate, could get it, but it will take hours and hours or days and days to really record it. In this size, it's about 1 meter 50 times 1 meter 50 or something like that. So we fitted this model manually. We took these primitive shapes to facilitate the process, and then we created ground truth depth maps, for example. So this is one set of ground truth. So then the problem was, okay, if we use LiDAR or manual measurements, or if we use UV paint as a Middlebury, that takes a lot of time. LiDAR especially, we scanned a room with LiDAR and it took a whole day just for 5 or 6 views, and we still had only a point cloud, and then we had to register the views partly manually, and that's a lot of work. It's not fun at all, and we want to create a lot of ground truth, not just a scan of a single room. So we thought about KinectFusion. And Carsten was at our lab, and I talked to him about that stuff, and suddenly we had a project. So what did we want to find out? We wanted to find out how correct is KinectFusion, how accurate is it? How does it compare to a LiDAR scanner or something? And we took 3 reference objects. One is 30 centimeter large. We scanned this with a structured light scanner, which is like 50 microns accurate. I hope this is 50 microns. I always mix this zeros up here. Then we have this box. I already showed it to you. And finally, we have this LiDAR scan of our office. This is one of our offices. And here you see this is a volume of about 7 meters by 7 meters by something. And then we used KinectFusion to actually scan these rooms, and we compared the accuracy. And here you already see, okay, for such small scales, it doesn't really work well. So we had a look at the errors. Here you see the scaling. So up here, blue is a small error, red is a high error, and then you have these 8 millimeters, 15 millimeters, so different scalings. Here you see there are small errors actually, but the detail isn't captured. So this is the lower limit of what we can get with the current Kinect. The current Kinect has a minimum distance of 0.8 meters. And this is one limiting factor, and it might also be other factors. But in this box we saw, okay, the errors are about 50 millimeters. We looked at the statistics, here you see the full statistics. Here for this room where we only had the point cloud, we couldn't compute the distance to the mesh, so we had to compute the distance to the nearest vertex. I'll argue about that. But you see that the mean here the mean is about 5 centimeters here. And here 10, and here we have a 9 millimeter accuracy. Then we see the problem of this LiDAR scan. The LiDAR scan is only 5 to 10 millimeter accurate, so we are in the order of the same magnitude. So this is just a sanity check whether we are in the right location. And oh no, here I was just wondering why is this error so high? No, it's meters here, and I have to look it up again. I'm not sure about this. I think we get here, we have this 0 to 50 millimeters errors, and you see all these errors at the boundaries of the object where we don't have actual data, and this is kind of a problem. But with this box and with this feasibility or sanity check, we can see we can get around 10 millimeters accuracy, I would say. That's very interesting. And this was one important result, I think. And the next question was, okay, can we improve the quality? So we still are in the range of 10 millimeters, sometimes more. It's a statistic. We have a median or an average, but that's not all we need. So the limits of Kinect are there at least. So we thought, okay, let's take time of flight. Time of flight has 200, this one has 200 by 200 pixels size. This is compared to full HD, roughly full HD. So we tried to upsample this and found that doesn't really work that well, so we had to do sensor fusion. So what we took, the original image, just scaling it up looks like that. Next version is using something like SGM. This is SGM, semi-global matching. It's just using the stereo information. We have lots of systematic problems, for example, in this region here. Now we take the time of flight data and use this as input for a stereo block matcher only. It's just try to be as simple with the algorithms as possible and as complex with the hardware as we need it to. So that's what you see. And if we then regularize this with a second order TV, we'll get something like this. So this is our next approach. So perhaps you have better data here. We compared this with ground truth. We found out we do get some relatively good results, but the error is in the order of centimeters now for a single view. If we take KinectFusion, put this into the pipeline, we hope we get smaller errors. On GPU, this takes here 2 seconds per frame, and the global method 90 seconds per frame. But then we still need materials, we need light sources, we need sensor simulations or renderers, and this is something we cannot do. So we do have this light field project going on by other guys at the HCI, Mr. Goldbücke, Sven Wander, Markus Jeder. They are currently trying to play around with these Stanford-like gantries. We acquired 2 Raytrix pan-optic cameras. We built this LiDAR, this light dome gonio-reflectometer, which is here you can change the light source. You can also so you can basically change the spectrum. It's relatively fast, and you have only one camera and different rotation angles. Problem is calibration. We will see how far we get with this. And then we try to build specialized hardware, like for example this depth edge camera, which is based on the work of Raskar in SIGGRAPH 2004, but we use a color camera and multiple light sources, and we get these contours on an object, and from these cast shadows we can find the discontinuities of the depth, which is also very interesting because discontinuities in motion very often correlate with the discontinuities in depth as well, and we can try to use this information to create better ground truth. And one point I left out completely, this is my conclusion, one point I left out completely is this interactivity stuff. I dropped it for today because I can't show many results on that. But we also thought, okay, if optical flow computation or segmentation or any other correspondence estimation would be really interactive, so we have the user in the loop and we can afford that, we can get much better results. So to conclude my talk, ground truth generation is are a lot of trade-offs, and there are many options, and there are different kinds of ground truths, and we have to decide what we need. We have quality versus quantity. How much ground truth do we need? How good does it have to be? We have geometry versus radiometry. Do we really need to take into account this information, the light fields or whatever? We have hardware versus software. We can build hardware systems which record the ground truth, which are very specialized and extremely expensive, and then we can try to see whether we can get this with a small camera. Speed versus accuracy. Our algorithms for ground truth generation can be slow and can have a human in the loop. Measurement accuracy is important for real data, and predictive rendering, like having physically correct models, is important for having synthetic data. Or is it? We don't know. And then finally, generalization versus specialization. I think this is a very important point. If we estimate optical flow for a given application, we can really tune this model we want to fit to the data for this application. If we don't know any application, if we want to have a generalist model, it will not perform well on all. It will not perform well on all these specialized cases. There will always be some average quality algorithm. So that's it. Thank you very much for your attention, and I hope there are any questions.